Okay, in this example, we're going to demonstrate how we can generate a square wave using a whole bunch of sine waves in terms of signal generators. So what I'm going to do is add some signal generators here so this is source. Signal generators are found here. Let's see, a sine wave. There it is. Okay, so there's a sine wave there. We're going to duplicate, let's say, up to 11 harmonics. So we'll copy this guy, then paste again, paste. So there's the fundamental, the first, third harmonic. Put this as the fifth harmonic. There, seventh harmonic. Okay. Paste. Okay, so that's 1, 3, 5, 7, 9, and we'll do one more. And paste. Alright, we're going to change each of these. We'll make this 1 hertz. So we'll multiply this by 2 pi. 1 times okay, that's just amplitude of 1 and times 2 pi, and we'll multiply this 1 radian times 2 pi. So this is 1 hertz. Okay. Now we're going to do the same thing here. Change this to 1/3 the amplitude, and this is 3 times 3 hertz times 2 times pi. And this is 1/5. This is 5 times 2 times pi. So what I dragged here are a couple of signal generators and a summer. But you can see I have how many signal generators? 1, 2, 3, 4, 5, 6 signal generators. So here's the fundamental. One has an amplitude of 1, and this is 1 hertz, where we put this in radians since that's what's required from the Simulink in MATLAB. Alright, so we'll cancel that. Take just for your third harmonic. So this is 1/3 the amplitude with 3 hertz. This one is 1/5 the amplitude of the fundamental, and the frequency should be 5 hertz. So we'll put 5 times 2 times pi, and we'll change that to 0 right there. Press OK, and we're set with that. We'll check this one. 1/7, 0 bias, 7 hertz. And this should be 1/9 amplitude, 9 hertz. And this should be 1/11 and 11 hertz. So let's close this up. Excuse me. Alright, now notice we need 1, 2, 3, 4, 5, 6 inputs right here. So we'll change the summer right here to add 6 more pluses. 1, 2, 3, 4. And then we'll just feed that as the input. Okay, then we'll put a output, so that's a sink. We'll use a scope, feed that as the output, and there you have it. So we'll take a look at the scope. This is where we're going to display it, and then we're going to run it right here. Okay, and scope looks like that, and that's our 1 Hertz display. Well, I'm just changing the simulation to 1 second, so I went from 10 seconds to 1 second. I made the change right here, and here's the result of the output from the scope. So you can see here that a square wave can be generated from a whole bunch of sinusoidal signals, and that this should demonstrate the Fourier coefficients. Once again, let's say this is a 1 Hertz signal, and if I want to transmit a square wave, it requires a bandwidth from 9 to 11 Hertz in order to duplicate this square wave. Alright? Whereas if we just want to generate, let's say, just a fundamental frequency, the bandwidth of the signal requires only 1 Hertz. And if I want to generate all these signals, we need a bandwidth of the highest frequency. In this case, it would be 11 Hertz. And therefore, our square wave is generated from these set of signals. And hopefully that demonstrates the concepts of Fourier coefficients, where this is the fundamental frequency, has an amplitude of 1. This is the third harmonic, which has an amplitude of 1/3. This is a 5 Hertz signal with an amplitude of 1/5, 1/7, with a frequency of 7 Hertz, one amplitude of 1/9 with a frequency of 9 Hertz, and finally an amplitude of 1/11 with a frequency of 11 Hertz. So if you do your Fourier coefficients, you can generate these type of square waves. I encourage you to try other waveforms and see if you can get the same result using this MATLAB approach.